Determinants and elementary operations. This section is very neat. I like it because it's one of the ways that I find the determinant by hand that I think is a whole lot more efficient than cofactor expansion, and that is to find the determinant by elementary row operations. But you got to be careful here, and let me show you. They have here some properties for a theorem that shows you what you need to watch out for. Well, first, if a matrix is square, and if that matrix A has a row or a column of all zeros, then it's easy. The determinant is equal to 0. Okay. Now that also begs the question that if there are two rows that are multiple of each other, well, you can cancel out and get a 0 for an entire row. Thus, that determinant as well would be 0. Or if there's two columns that are multiples of each other, there again, that determinant would be 0. Now here are a few of the properties necessary to being able to find the determinant by elementary row operations. And you gotta hold my hand here, especially I think for the first one and the second one. That third consequence. Everything kind of the milk and everything that's in the milk kind of blends in together for that third one. So you just drink the milk and it's okay. That's probably a bad analogy. Here for part A, again, let the matrix A be a square matrix, n by n matrix. If B is a matrix that results from a single row or column of A being multiplied by a scalar k, then the determinant of B is equal to k times the determinant of A. Now I'm giving an example here to kind of show you what this particular theorem says, and what they're trying to say is that you should be able to easily get the determinant if you know something about how the rows are fixed up, or the columns are fixed up for a particular matrix. So here, if we have some matrix A, and then, oops, that's not supposed to happen. We got some matrix A, and notice that the only difference between A and B is that B is the first row of B is multiplied by -5. If you take out that -5, then you basically have -5 times the so-called determinant of A. So, in a sense, if I know the determinant of A, I can just multiply -5 by it, and that gives me the determinant for B. And that's what I'm showing you here. The determinant of A comes out to be -2. The determinant for B comes out to be, work that out, that's 10. But that's the same thing as, based on this particular theorem, that's the -5 here times the -2. Right. It's that -5 that's taken out of that first row times the determinant of A, which is -2. So we just get +10. Now, in one of the textbooks, it's kind of, like a standard example. It's kind of shabby, I think. Yeah. I think the best way to see it is when we start working a problem, and then I think it makes sense, okay? So forgive me while I indulge in some preliminary exercises. If B is the matrix that results when two rows or two columns of A or interchange. So here, if you're reducing, and here's what they're talking about for theorem A, theorem part B, they're just really saying you're reducing a matrix in row reduction form, looking for the determinant. And when you do that, if there's a row, part A, if there's a row that has a common factor, for that determinant, you're going to factor that term out and multiply it times the determinant. Now, for the determinant, if you interchange two rows or if you interchange two columns, you're going to negate that determinant. So that's what I'm showing you here with matrix A and matrix B. Notice the difference between matrix A and B. Row 1 has been interchanged with row 2. But look at the determinant. Matrix A determinant is -2 and matrix B determinant is +2. So the key is, if I know one, I can get the other for free, right? That is, if I know something about that particular property. So I just get the determinant of A and just negate it, and I get the determinant of B. Now, part C, it was the one that I said in the beginning that it just kind of washes out in the milk. If B is the matrix that results when the multiple of one row of A is added to another row of A, then the determinant of B is equal to the determinant of A. There's no change. Basically, for A, B, and C, all we've done was just to walk down through the 3 elementary row operations. Now, check that out. Now, the elementary row operation says that 1, you can multiply any row by a non-zero scalar. Here, for the determinant, when you multiply or factor that guy out, you better actually factor it out and multiply it times the determinant. That's how that changes. If you, the second elementary row operation says that you can interchange rows or you can interchange columns. But for the determinant, if you're looking for the determinant and you're doing row elementary row operations, you better negate that determinant. And then the third elementary row operation says that I can add a multiple of one row to another row. Here, for the determinant, it's not even changing. So that's pretty cool there. And I give an example here. So the matrix A, and then let B be the matrix that results from A from the operation. I want to say -3 times row 1 plus row 2. And so that gives me this new matrix, right? So I did that. Now, the determinant for A is 4 minus 6, that's -2. But look at B. B is it's a triangular matrix. So the determinant for B is -2. No change to the determinant. Pretty cool. Now here's where the work begins. I made mention of this above, but just want to make it formal. If a square matrix A has a multiple of 2 rows or 2 columns or multiples of each other, then you get for free the determinant is equal to 0. Now, here's an example for matrix A. Row 2 and row 3 are multiples. Row 2 and row 3 are multiples. Huh! Who would have seen that? Okay. Well, I see it, yeah. Row 2, multiply 2 times it, we get 6, 10, and 4. Well, there we go. So we use that theorem. Yeah, the determinant is equal to 0. We go home. Good. And made mention of this in the last section. Always good to bring back up simple things, right? Determinant of a square diagonal or triangular matrix, the product of the entries along the main diagonal. So there it's just 2 times a third times 6. So that's 4. I have to always check my work, right? Alright, here's some problems. Evaluate the determinant of the given matrix by reducing the matrix to row echelon form. Now I worked this one out, so let's just talk about it. So I notice here that for row 1 there's a common factor of a 3, so I factored out the 3 from row 1. And I said 3 times the determinant. Notice these lines here denote determinant. So now my goal I want to do is to reduce the matrix to row echelon form, or now another phrase for that is upper triangular. So by doing that, then the determinant is just the entries along the main diagonal multiplied times whatever entry is on the outside of that determinant, right? So now what I do is I use this 1 to get rid of this negative 2. So just say 2 times row 1 plus row 3, and that gives me this determinant. And so now what I do is I interchange rows 2 and 3, and that negates the determinant. See that? So now this guy is a upper triangular, so the determinant is just the entries multiplied along the main diagonal. Don't forget, times that negative 3, and we get 30. Now this next one I'll work out by hand. Okay, so I'm going to interchange rows 1 and 2. So it's negative. This is 1, 1, 2, 0, 3, 1, 3, 2, 4. Alright, so now I'm going to use this 1 to get a 0 where that 3 is, right? So we do that by simply saying negative 3 times row 1 plus row 3. That negative stays out in the front. This is 1, 1, 2, 0, 3, 1. This is 0. Negative 3 and 2. Negative 1. Negative 6 and 4. Negative 2. Alright. Very good. So now I want to try to make this upper triangular, so I'm going to interchange rows 2 and 3. To do that, this is going to be negative times a negative 1. So it's just positive. And what I want to do is to use that negative 1 to get a 0 where that 3 is. So we'll just say 3 times row 2 plus row 3. So this is negative 6 plus 1 is negative 5. Now this is triangular. So I just multiply the entries along the main diagonal. Okay. The party is over. There's no more fun. Dang. Well, I'll see you later.